Welcome again, and we will continue our explorations with the forced oscillator, and in particular today's module we will look at Q values once again for forced and damped oscillator. So, we wrote down the equation of motion for a forced and a damped oscillator. Turns out that it is a non-homogeneous second order and ordinary differential equation. That is the kind of description. So, it is a class of differential equation, and we know from mathematical considerations that equations of this type have two parts to their general solution, which is shown here. So, x of t is the general solution. It has two parts, x of x c, which is called the complementary solution, which is simply the solution of this equation with the right hand side being 0, corresponding to the statement that there is no forcing, f 0 is equal to 0, and x p is what is often called the particular solution, which could be in general any one solution for this full equation. Now, of course, there are many ways of getting this particular solution. Again, we will not be getting into how to do that. If you pick up any differential equations book, you should be able to see at least 2-3 different ways of finding any possible solution for this class of differential equations. We are essentially physically motivated. Okay. So, if you look at as a physical problem, you could attach physical meanings to both these parts. X c in a more physical language would be called the transient, the kind of dynamics that would vanish after sufficient amount of time, and particular solution would be what is called the steady state solution. So, you are interested in solution which lasts for infinite times. So, steady state is what you would reach as time tends to infinity. So, as far as we are concerned, we are interested in the steady state solution for this problem. Now, let us, since we have already worked out the solutions for this, and it turns out that the steady state solution is simply oscillatory solution with the same frequency as the driving frequency. So, my driving frequency is this quantity, which is omega. So, you are driving an oscillator with the frequency omega, and the oscillator responds by oscillating with the same frequency omega once you give it some time to relax. So, just to show how possibly it might look physically, let us just quickly plot the solution. X as a function of t, plot it as t. So, what you might see is maybe something that initially looks very different and so on, but finally you will notice that it is settling to some oscillation whose frequency is same as omega. So, for instance, from here to here, maybe you could say that these are transients corresponding to the so called complementary solution, and from here onwards you are in the regime of steady state. I have not drawn it very well. So, it represents oscillation with frequency omega. So, this is what happens in a forced oscillator. So, we will come to what we are going to do today. So, we will look at finding Q values for the forced oscillator, and we already met this quantity Q value when we looked at the damped oscillating systems. So, here again I have the equation of motion here written down, and this is displacement as a function of time, and this is velocity as a function of time. So, the first thing I want to, even before I get to q value, the first thing that I would like to do is to compute the power supplied to the oscillator by the driving force. So, if I am driving by this force f 0 cos omega t, how much power am I giving to the oscillator? So, that is the quantity that we will first compute, and then we will look at the q value. So, the instantaneous power at time t would be the would be force multiplied by the velocity. So, force imparted at time t and the velocity of the system at time t. Now, we know the quantities on the right hand side, we just need to put them together here. So, P of t would be f of t, which is f 0 cos omega t, that is my driving force, multiplied by velocity as a function of time. So, again we go back to our velocity, which is f 0 by modulus of z into cos omega t minus phi. So, I have a formal expression for instantaneous power, but maybe what I would like is the average power. So, this is the power at a particular instant of time t, but a more useful quantity is what is the power supplied over an entire cycle of the oscillator, over one full time period. So, the average power, I just need to integrate this over entire time period and divide by the time period. So, that is my formula for average power. So, it would be 1 divided by the time period. So, integrate this quantity p of t. Okay. So, you have these small chunks of time, add the power supplied at every infinitesimal time differences over the whole time period going from 0 to t. This would be my average power, and of course, it goes without saying that the quantity t is the time period of oscillation. And remember that in steady state, the angular frequency is omega, which is the frequency of forcing. Hence, this capital T should be equal to 2 pi by omega. So, now we have the problem set up. We just need to do one integral to be able to calculate this average p. And of course, this integral is not too difficult to do. In fact, you can split this integral into two parts if we expand this quantity cos omega t minus phi. So, let me do that. Average p would be f 0 square by t into this, and 0 to capital T cos omega t into cos omega t cos phi plus sin omega t sin phi into dt. So, it is now split into two parts, and the first integral essentially is cos square omega t dt integral, and the second one will be cos omega t sin omega t integral. So, for example, the first integral, to do the first integral, you need to be able to do this integral cos square omega t dt, where this one goes from the limits go from 0 to capital T, and capital T is 2 pi by omega. So, this is one integral for which we need to know the answer. The second integral for which we need to know the answer is 0 to 2 pi by omega sin omega t cos omega t dt. So, this is another integral which we need to do. It would be more easier if we also divide it by t. We are doing 2 pi by omega. So, I will encourage you to try and do the integral yourself. It's a fairly simple and straightforward integral to do, and if you do it correctly, the first of these integrals should give you the value half. So, clearly the contributions come only from the first part of the integral, which is this one. So, now you assemble together all the results that we have, we will finally get to this point where we have evaluated the power supplied to the oscillator over the entire time period. Okay. So, now I have computed the average power supplied to the oscillator. Where does this go? Of course, the oscillator is oscillating, but in the process of oscillation it is overcoming the frictional force, and it is expending this power in overcoming that frictional force. So, now we could ask the question, how much of the power is used up in overcoming the frictional force? Again, we will average it over an entire time period or an entire cycle. So, we are more interested in what is the average power that the oscillator uses up in overcoming the frictional force. I want to compute this quantity, average power consumed by the oscillator in one complete cycle. So, it means that the oscillator is overcoming friction and is doing work. So, essentially what I want to know is what is the rate of doing work against the friction. So, that will involve the frictional force, and we know what the frictional force is. So, the frictional force here is gamma x dot, and I want to know what is the rate of work done by this against the frictional force. So, that will be this multiplied by velocity. More correctly, work done would be simply frictional force multiplied by dx, and of course, we want to know the rate of doing work, hence it is dx by dt. So, this would be gamma x dot multiplied by x dot, which is equal to gamma x dot square. So, what we have is an expression for again instantaneous power that is consumed by the oscillator. We will do the same trick again. You compute this quantity over the entire cycle. Let me use the symbol average power with the d in the subscript to indicate the average power that is dissipated by the oscillator, and this would be again 1 over t going from 0 to t. You integrate this quantity gamma x dot square dt. X dot is something we already know. X dot is simply the velocity which is given here. We just need to plug in this expression for velocity, do the integral, and we should be able to get it, which is what we will do now. And so, I will have gamma I can take out 0 to t, x dot square that would be f 0 by mod z cos square omega t minus phi dt. So, this can be further simplified. Average P, average power dissipated, is equal to gamma f 0 by t into modulus of z 0 to t cos square omega t minus phi. So, if you remember, this is the integral that we already did. So, we should be able to just use this result back in here, and if I do that, the final result would turn out to be the following. It will be gamma f 0 square. Okay, I missed out power 2 here. It should have been square here as well. f 0 square divided by mod z square, and the integral value with 1 by t will give me half. So, that is 2 here. Let me remind you that our basic definition of impedance Z was this quantity gamma plus I multiplied to m omega minus s by omega, and from here modulus of Z of course was gamma square plus this, and we also wrote down a relation for tan phi, which is m omega minus s by omega divided by gamma. So, if this is tan phi, we could also write expressions for cos phi and sin phi, in which case cos phi would be equal to gamma by mod z, and of course, sin phi would be equal to m omega minus s by omega whole thing divided by mod z. What we really need is this quantity, an expression for cos phi. Let us go and look back at the formula that we have for the average power dissipated. Let me rewrite it as f 0 square divided by 2 times mod z multiplied by gamma times mod z, and we know that gamma times mod z is simply cos phi. So, I can go back and write this quantity as f 0 by twice mod z multiplied by cos phi, okay, and that is simply our average power dissipated. Now, this is remarkable because if you compare this result with what we have here, these two results, you will see that they are exactly identical. So, you are supplying some power to the oscillator by a mechanism of the external forcing. Okay. The average power supplied to the oscillator over an entire cycle, over one complete cycle, is equal to the average power that it dissipates over the same cycle. So, in other words, it does not really hoard the power, it does not store it for future use. So, the average power given to the oscillator is immediately spent up over the same time period. So, this two quantities are identical. So, this is our central message in this part of the section. Now, we will use this quantity average power to define Q value. Before we define the Q value, let us sketch this function as a function of the driving frequency omega, because that is going to tell us how much of the power is being absorbed at different frequencies. I am going to choose some value here as omega equal to omega 0. In fact, you will notice that when omega equal to omega 0, that would be the case when cos phi is equal to 1, as we shall see now. And clearly from the formula that is written down here, the average, the maximum of the average power, which I indicate by average P max here, would simply be equal to f 0 square by twice mod z, corresponding to phi being equal to 0, in which case cos phi is equal to 1. Now, you could ask what is phi being equal to 0 would mean. So, phi being equal to 0 would imply that m omega minus s by omega is equal to 0, and this implies that omega square is equal to S by m, which is equal to omega 0 square, which is what we call the natural frequency of the system. So, when the driving frequency is equal to the natural frequency of the system, the average power supplied to the oscillator is maximum. So, at omega equal to omega 0, this function is going to have its maximum value, and because the denominator here is quadratic, the function would essentially drop off like this. This tells us physically that maximum power is absorbed by the oscillator when the driving frequency matches the natural frequency of the system, and also it tallies with the earlier resonance idea that we saw, that at the natural frequency, when you drive it at the natural frequency, the amplitude of velocity is the largest, and the amplitude of displacement is nearly the largest when you are driving it at the natural frequency. And of course, if a lot of power is being absorbed by the oscillator at omega equal to omega 0, it also dissipates the same amount of power over every cycle. That is the general result that we saw just now. So, if you want a large sort of response from the oscillator, you should drive the system at the frequency corresponding to the natural frequency of the system. Sharper the curve, more the power is given to the oscillator, and it is likely to sustain oscillations for a longer time. So, hence you could say that sharper curves of this type would correspond to larger Q values without doing any calculation. Let us see if that is true. So, I have the same curve here, average power as a function of driving frequency, and what I would like to show is the following, that Q is equal to omega 0 divided by omega 2 minus omega 1, where this two quantities omega 2 and omega 1 are defined as follows. So, let us define a value which is half the value, half the peak value, which might be somewhere here. So, this quantity is half of the maximum value, and the two values of omega 1 and omega 2 are so defined that omega 2 is this, omega 1 is this. So, in general this curve is a symmetric curve about omega 0, but it is my poor drawing that it looks as though it is not symmetric. So, my Q value definition says that it is simply omega 0, which is the value of driving frequency corresponding to the peak power being supplied to the oscillator, divided by this width, which is often called the full width at half maximum. That is the definition of Q value in this case. Now, let us see how we get to this. Our starting point is the definition that Q value is defined in terms of these two, omega 1 and omega 2, which corresponds to two values of frequency at the same value of average power, and the same value being average P max divided by 2. Okay. So, at this value there are two possible values for frequencies. So, you draw a horizontal line from here, it cuts the resonance curve at 2 points. So, you draw two vertical lines, you will get this omega 1 and omega 2 corresponding to that. So, this is our definition for defining omega 1 and omega 2. And once you know omega 1 and omega 2, it defines the width, and that would tell us what Q factor is. All we now need to see is whether this definition of Q factor or Q value coincides with the definition that we already had earlier on. Let us start by implementing this condition. So, the left hand side is average power, we derived this result. So, that will be gamma f 0 square by 2 mod z square, and the right hand side is the maximum of the power supplied divided by 2. So, that is half into f 0 square divided by 2 gamma. So, remember that we had this relation for maximum power supplied. So, this is the condition that we have, and if you cancel out various things here, because for example, this would cancel out, 2 would cancel out. So, things would cancel out, and this equation would simply reduce to average of z square is equal to 2 times gamma square. And now, let us go back to the definition of modulus of z square, which we can just get from this relation here. If I put in that relation, I would get, from here we are just 2 steps away from what we want. If I further simplify it, it will be m omega minus s by omega whole square, that is equal to 2 gamma square minus gamma square, hence simply this, and this would imply that m omega minus s by omega is equal to plus or minus gamma. So, let me write it out as two different equations, m omega minus s by omega. One possibility is that it could be plus gamma, other one is m omega minus s by omega is equal to minus gamma. We know that there are two solutions corresponding to omega 1 and omega 2. So, if I put in the 2, so let us say that one of them corresponds to omega 2. So, I will have m omega 2 minus s by omega 2 is equal to gamma, and the other one let us say corresponds to omega 1 solution. So, I will have m omega 1 minus s by omega 1 is equal to minus gamma. Now, I want to eliminate s here, s is the stiffness constant, and the way to do is simply multiply this equation by omega 2, multiply this equation by omega 2 and multiply this equation by omega 1, subtract one from the other, and we will be able to eliminate s from the two sets of equation. And once we do that, I will leave it to you to do that small piece of mathematical step, and once we do that, we will get omega 2 minus omega 1 is equal to gamma by m. And now it looks like we are getting close to the result. Now, I will divide both sides by omega 0 and just invert it, in which case you will get m omega 0 by gamma is equal to omega 0 by omega 2 minus omega 1. And what we know from what we had already studied is that this quantity here is simply equal to the q value. So, I have my final result that q value or q factor is equal to omega 0 by omega 2 minus omega 1, and this is a very practical definition that you can get whenever you look at the resonance curve in the form of average power supplied as a function of the driving frequency. So, this omega 2 and omega 1, just to remind you once again, are the two values of driving frequencies at which the average power is half the peak power. So, there is one another way of looking at q value in terms of what is called the amplification factor, and we will soon realize what it means, but let me go through the procedure itself. So, to begin with, you might recall that the amplitude of displacement for a forced and a dissipating oscillator is given by this expression. So, we derived it in one of the earlier modules, and at resonance, let us call the resonant frequency as omega r. So, omega r is my resonant frequency. And we also saw that resonant frequency, what I call as omega r, is simply equal to this expression, and we repeated that it is slightly lower than the natural frequency, which is given by omega 0 or omega naught here. Okay. So, now the maximum amplitude, or let me call that quantity A max. The maximum amplitude that you can ever get would be f 0 divided by, you replace omega by omega r times mod z. Okay. So, this is the maximum amplitude you could ever get for the set of parameters that you have chosen for your oscillator. Now, let us also define another reference quantity. So, all I am going to do is to measure A max against a reference amplitude, okay, and that reference amplitude, let me call it some A 0. And how do we get this reference amplitude? So, what I am going to do is to look for amplitude in the limit that driving frequency tends to 0. So, you take the limit that driving frequency tends to 0 for the amplitude of displacement. Now, when you take the limit omega tending to 0, among the various terms in the under the square root, the one with omega in the denominator, this term, that would be the most dominating term, because you are taking the limit of very small omega, in which case this expression would simply be f 0 by omega into, and in comparison with s by omega, gamma square would be small. So, we can neglect that. So, I am going to have s by omega here, omega and omega would cancel. So, this would finally give me f 0 by s. Remember that s is a stiffness constant. So, in the limit of omega tending to 0, my reference amplitude is A 0, which is f 0 by s, and this reference amplitude, as you can see, is independent of omega itself. So, now I have two things, one is this quantity A max and the reference amplitude which is f 0 by s. what I am going to do is to take the ratio of A max to A 0. So, let me start by writing A max by A 0 whole square, and I will just copy the expressions that I have written down here, in which case, and before I take the ratio, this can actually be further simplified. So that this will be omega r into gamma. Essentially, we have just put in the condition for the resonant frequency. So, now I need these two quantities, A max and A 0. I am going to take their ratios. Okay. So, I have this ratio between A max and A 0. Now, we will manipulate it a bit to write it in terms of q values. The next step is to cancel off f 0 square, and remember that omega 0 square is equal to s by m. I can replace s square by omega 0 to the power 4 into m square divided by gamma square, and omega r square is the expression that we already have here, which is omega 0 square minus gamma square by 4 m square. So, from here on you will see that in this expression the only quantities that are involved are the quantities which we normally use to define our q value, which is m omega 0 by gamma. So, it becomes very easy to manipulate this to write it in terms of q values. So, in a very straightforward way, you could write A max by A 0 to be equal to q square divided by 1 minus 1 by 4 q square. Further, you take off the square root from here, and that will give me q divided by square root of 1 minus 1 by 4 q square. And now, we will take the limit that q is much greater than 1, meaning that we are working in the limit or in the regime of parameters where q value is very large, in which case this expression here becomes approximately equal to q. So, this is our required expression, that A max by A 0 is q, and remember that A 0 was f 0 by s. Now, we can sketch this the resonance curve in terms of the q values. So, for instance, here I am plotting x max as a function of the driving frequency omega, and it might look something like this. So, this value could be the reference value, which is A 0 equal to f 0 by s, and every other peak here is written in terms of this reference value A 0. For instance, this curve could be the case of q equal to 2. So, which would mean that the peak here is twice this value, and so on. So, we can draw some more curves like this, and this could probably be q equal to 3, and so on. So, you would notice that larger the value of q, sharper is the resonance, and the resonance width, which is the value of this width at half the peak with respect to, let us say, this point, with respect to this peak, it gets narrower and narrower as q increases. So, this is another way of understanding the q value as telling us about the amplification factor, but ultimately it relates to the same meaning in terms of the original meaning that we had seen earlier. It simply at some level tells you how much of energy that you put in is sustained by the oscillator. Okay. If the oscillator can sustain it for long enough time, then you would say that its q value is large. So, just to summarize what we have been discussing in today's module, we obtained this first and important result, that the average power supplied in one cycle is equal to the average power that the oscillator dissipates over the same cycle. Effectively, it does not store the power for future use, and we were able to show that the q value, which we already saw in an earlier module, can now be defined in terms of the width of this resonance curve, and q value is equal to omega 0 by omega 2 minus omega 1, where omega 2 and omega 1 correspond to two values of driving frequencies at which the average power supplied is half the peak value. And finally, we were able to show that q factor is simply the ratio between the maximum amplitude divided by an initial amplitude. And we will see some applications of all these concepts in the next module.